The paper I will be introducing to you is named TESL, a model for metric time and for modeling and simulation. And this joint work has been conducted with Frédéric Boulanger and Burkhard Wolf, all coming from Université Paris-Saclay and Centrale Supélec. The context of our problem lies in software and systems today being deeply software intensive. And the question we attempt to address is how can we design their expected time behavior? The first challenge we had in mind is to model different types of paradigms. In this example, which is extracted from Boulanger of a car power window, we have three components: an input button, a microprocessor, and an electromechanical part. The communication between those three components is made by means of a bus. And in fact, it is possible to model the communication between an input button and the bus with discrete events. Also, it is possible to model the microprocessor with time finite state machines. And finally, we can model the electromechanical part with synchronous data flows. So the question here is that if we want to model the whole system, we need to combine these different paradigms. The second challenge we had in mind is to consider different time frames. Indeed, in a whole system, different subsystems may have different time frames, which may be flowing at different rates. In some cases, it is possible to define an arithmetic relation. For instance, here between a satellite and a ground receiver on Earth, but sometimes it is not possible to do so. And hence, we will say that there is no global clock. Our study has started from the modeling and simulation framework, which contains an inner language, which is called TESL, and which is the subject of our survey. The goal is hence to model time and causality, model different types of paradigms of these heterogeneous parts, and allow the coordination in terms of metric time between these heterogeneous parts in order to design event-triggered and time-triggered behaviors for simulation and testing purposes. The language in question is named TESL, that is the tagged event specification language that I will be introducing to you. This language deals with execution traces. And in an execution trace, we have clocks, which are depicted by the horizontal bars, and which denote the timeline of events. We also have timestamps given in green, and which denotes at which time the event is occurring. We also have the red rectangles, which denote ticks, and which denotes the fact that the event is occurring or not. And finally, an instant is a discrete observation of such kind of continuous system. And a run is hence a sequence of these observation instants. A core fragment of our language is depicted here. We have a synchronous implication. For instance, kmaster implies kslave, which states that each time kmaster is ticking, the clock kslave will be ticking instantaneously. We also have kmaster sporadicto, which says that each time kmaster will be which says that kmaster will be ticking once and at some timestamp too. We also have a time delay, which is given by a duration delta t from some kmaster clock to a clock kslave. And finally, we also have time relations between time frames of clocks. Please note here that in this case, we consider time delay by means of a metric duration, and we are not counting ticks as would be done, for instance, in temporal logics. Let us start with a running example of the radiotherapy machine. In this case, we consider that the patient receives prescription for cancer treatment with the amount of radiation of 2 grays at some low dose rate of 1.5 gray per hour. To model this process in our setting, we start with 5 clocks. A clock for time itself, so hours, another for the quantity of radiation grays. We also have a clock for start, so start means that the machine is starting, stop that the machine stops, and EM stop, the fact that the machine stops for emergency. And we have a time relation between both quantities of gray and hour of the low dose rate of 1.5. We also have the fact that each time the machine starts, after a delay of 2.0 on gray, it will be stopped. And finally, each time the machine will be stopped for emergency, it will have to stop instantaneously. Let us start this simulation with a simple example. In this normal execution, we start with time being 0.0 on hours, and hence the quantity of radiation is still 0. At the next instant, the machine will be stopped whenever the quantity of radiation is 2.0. So at this point, it would have been 1.33 hours. This is a normal execution of the machine, but this is not the only way to execute it, in fact. Indeed, it could have been also possible to declare an emergency stop at 30 minutes. That is, that the quantity of radiation dose would have been already delivered is 0.75. And at this point, as the emergency stop has been triggered, the machine would have to stop instantaneously. We can see here that the number of possibilities of satisfying runs for this specification is hence infinite, and that this specification allows various kinds of interleavings. Another property that can be shown on this language is stutter invariance. Indeed, it could have been possible to consider other clocks, but which are not displayed in the execution trace. Here we have a clock which is named refresh, and which shows some refreshing process which is occurring periodically. And in fact, this stutter invariance property simply states that it is possible to take any execution trace, any run, and dilate it in order to preserve satisfiability and inject other clocks. Another important property we have on this language is polychrony. If we assume that we have another computing unit, for example, OX, and which has some event occurring at 0.5, the question that we are wondering is when does 0.5 occur? Does it occur between 0.5 hours, or maybe simultaneously, or maybe after 0.5 hours? And in fact, any of these combinations is satisfying, as we have not specified whether time on OX should be flowing faster, slowly, or at the same rate with respect to hours or the other quantities. And hence, we can depict this fact by means of time islands, which show how clocks are related or unrelated. Here, clocks between hours and grays are related and hence belong to the same time island, while OX is independent, and in this global system, we therefore have no global clock. To consider the this obvious infinite number of possibilities, we have hence started our study by means of a denotational semantics. That is a mathematical function which describes the set of denoted runs. It is an accurate and simple mathematical representation of what we require from our system, and also trivially provides compositionality, but is unable to derive runs in a constructive way. And for this purpose, we have designed an operational semantics, which is small step, and which is based on symbolic runs containing Boolean and arithmetic constraints. The idea in this is to describe time as a past, present, future pattern and unroll it. The present and the future components will contain these TESL formulas, and the goal of the game is to eliminate these formulas to produce smaller ones, smaller primitives into the past. And doing so will be constructing our runs and hence executing the simulation. We have brought two kinds of extensions to this language that is the core of our paper. The first extension is the precedence operator, which simply states that if an event is occurring on some clock C1, it will have to occur before it does on C2. And this is found in the TESL specification language and is particularly useful for modeling, for instance, timed automata. Another operator which is useful is the previous operator, whose semantics is to refer to the previous timestamp of the previous instant, and which is found, for instance, in Lustre, STRL, and is also particularly useful for modeling feedback systems, for instance, PID controllers or differential systems. Let us illustrate this second operator with a PID controller. In this controller, we have three parts: proportional, an integral, and a derivative, which are controlling a process plant. And the goal is to bring some measurement closer to a set point reference. For instance, if we are driving a car and we have set the cruise control on 90 km/h, we would like the car to control the gas pedal to accelerate or decelerate to keep the same constant speed. To proceed so, we can model this kind of controller by defining time relations using the precedence operator that we have defined previously. And we can see here that we have the proportional. We have the proportional, the integral, and the derivative parts, which are shown in the output, and which are controlling the process plot. If we plot an example, we can see here that the set point that we have chosen is 40, and that from 0, the process is brought to 40 with respect to time. To summarize, we have introduced TESL, a language to coordinate heterogeneous submodels, which is able to consider time in its whole nature, that is by mixing logical but also metric time on the other side, which is able to define synchronous and asynchronous constraints, which considers also polychrony, that is the fact that we have no global clock by default, where time can be also polymorphic, that is the time domains may be of various types, and which has been formalized into a denotational and an operational semantics, and hence provide good expressivity to model various kinds of systems. Thank you very much.
Thanks. So you can now unmute yourselves among the participants if you have a question. Okay, so then I would like to ask you, what is the complexity of reasoning this language?
Well, the complexity that we have, if we define in particular these kind of clocks which are polychronous, that is that we have no global clock is exponential, because we have to take into account this number of interleavings, and it is unavoidable to have this exponential. However, in our operational semantics, we were able to define symbolic runs. So these runs could be concretized, and these symbolic runs can reduce in a drastic way this complexity, but still remains exponential in our experiments.
Yeah, I mean, I can imagine, especially if the encoding of the numbers is binary. This is very common for any type of
And
language.
so to tackle the issue of complexity, in the experimental solver that we had, it is possible to define policies of execution. So the solver will be delivering one run according to some policy. For instance, time has to be flowing as fast as possible.